Okay, so the plan is to take a basis, whatever kind, and turn it into an orthogonal one. And then we turn it into an orthonormal one. That step is easy. We just divide through by the lengths. Turning it into an orthogonal one takes a kind of a strategic approach. As I said, sometimes we'll get them for free in a very important kind of way, but sometimes we have to just kind of attack the problem. So this is a fairly, it's not a beautiful method. I mean, it has projections that's very nice, and we'll see that there is a factorization that comes out of it. But you'll see it's sort of cold-blooded, right? The way it works is just like boom, 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 chop, chop, chop. All right. And there isn't necessarily a right vector to start with. So we usually just start with the first vector we're given. Here's a set of basis vectors. We tend to just sort of approach it in that way. We'll take the first one and then clean up the second one, clean up the third one, clean up the fourth one, right? So we could change that strategy around. But that's all we need to know for now. All right, so this is the notation we'll use. So we start with a basis. Let me make it this one. So we're going to start with some basis here. That's in Rm. There are n of these vectors. And we're going to turn into an orthogonal basis. And we'll denote those by q's, right? And then, as I said, orthonormal basis, easy to do. We're going to put a hat on them because we simply divide by lengths, right? So that's what this is. So let's just say q sub I equals 1 divided by the length of the basis vector here. So it's just a length. We're just dividing through. Right. Okay? Fine. So the idea is here's the piece, we're going to incrementally, or step by step, remove parts of vectors. So here's a general formula for n equals 3. So this could be in arbitrary dimensions. We have a basis with 3 vectors, so it spans a subspace of 3 dimensions inside an m-dimensional space, right? So this is a 3D subspace in Rm. And here's the formula. So let's see if we can understand this. So we simply take the first vector, as I said, A1, and set it to Q1. That's going to be our first basis vector. The next one, A2, well, as we've talked about, it could have some of this A1 direction in it, and we want to clean that off. So what do? This is, we start with A1, and then this piece here is the projection. Let me use a different thing. This is the projection, right? The key thing in here is A2. This is the first projection work we did, projecting onto a line. Projection of A2, the vector, the second basis vector, onto direction described by Q1. So let's find the part that's pointing in the direction Q1. That's our first basis vector. We want everything else to be right angles to it, so we're going to take that out. All right, so we'll have a picture in a second and we'll see how it all works. And then Q3, same idea, so another projection. So these are similar projections. And the first one is onto the Q1 direction and the second one is onto the Q2 direction. Right, so we're building them up. So, and in general, right, so we'd have the nth step would be Q n equals an minus, and there'd be all this stuff. It'd be n minus 1 projections of an, right, the nth basis vector that we were given to start with, onto Q1, Q2, I'll just write it like that, Qn minus 1. So there's this kind of growing triangle of things, right? So there's only the first step is very easy. There's just one piece. Then there are two pieces in the second one. Right, so one piece here, two pieces here, three pieces here, and eventually n pieces here, n minus one, and the other piece, okay? Excuse me. Right, so we're using projections. We know something special about projections. So we're just going to move forward and then we'll have an example. We have this rather spectacular thing, right? So this is just a number. This is just one of the examples. Hashtags are confusing, I guess, these days. So this is a number, right? This is just some number divided by a number. They're inner products. But over here, this is an m by 1. This is a 1 by m. And this is a m by 1. Right? So this is an outer product. It's an m by m. This is a matrix. This is p, q, 1. Right, this is an outer product. Add that. Fill apart, outer product. Cool. This is cool. So that's going to be helpful for us in a little bit. So we'll rewrite this. So we'll rewrite those three steps. Maybe I'll show the whole thing. So this is the same. Q1 is A1 in both cases. And this is how we get to the orthonormal piece. Right, we divide through by the length of Q1. Q2, we're going to rewrite these other projections, right? 1, 2, 3 projections, right? Here, here, and here. We're going to rewrite them using this projection operator structure, right? So this is a projection operator matrix projecting onto Q1. Same thing here, but the Q2 direction. So they're little projection matrices, right? So they find the part of A2, they give you the part of A2 that's pointing in the direction of A1, or A3 in the direction of A1 and A2. And then we're subtracting them out. So what's left has to be orthogonal. So what's left here, for example, if we take A3, subtract out the parts of A3 that point in the direction of Q1 and Q2, then what's left has to be pointing in, we'll say is pointing in the direction of Q3, and it must be at right angles to, right? So this is guarantees that these new Q basis vectors are at right angles to each other. They're orthogonal. And this is good for theoretical sort of stuff. And in all cases, we come along at the end, divide by the length of the vector to get the unit vector, and therefore an orthonormal basis, right? Right. So what is happening? What is happening? 3 steps, if you like. So this is just the first two pieces. So, right. So we have, right. So these are not at right angles. Well, let's just say orthogonal. That's sort of our special word. Not orthogonal. So we project. Right, so this is, let me do this, so do it again. So this piece, this is the projection of A2 onto the Q1 direction, because this is going to be Q1, right? We're just, A1, we're just assigning as Q1. Okay, so we do that. So we remove it. So A2 was here. A2 is here, so we remove, right? So we remove, right, the piece in Q1 direction. Should write. I can write the words. Right. So now they're at right angles to each other, and the last thing we do is we divide through so that now they're unit length. Right. So make unit length. All right, so this is now orthogonal here in the middle. Orthogonal, basis. This is just a basis. Orthogonal basis, orthonormal basis. Good? Good. All right, so let's do it. This is sort of a, we have a formula for it, but there's a deeper understanding always available. All right, so here's just an example calculation. We've got these 3 vectors. They are in 3 dimensions, so they span all of 3 dimensions. I'm going to tell you that they are linearly independent. But nevertheless, we might want to clean them up so that they give us a nice, and something we can do. They give us a nice orthogonal basis still. All right, so let's do that. So the first thing is easy. We just assign, boom, right? The first new basis vector is simply 1, 1, 1. All right, good. The next one, so this is the projection, right? So here's, we start with A2 and then we trim off the projected part. And we're going to always use, generally for these calculations, we use the, right? We don't construct the projection matrix. It's a theory thing. We use these inner product pieces. So let's just do it. So we've got Q1, so they're always going to look like this, 1, 1, 1. We've seen these before. A2 is 4, 2, 0. Look a little bit funny. And then we'll have the dot product on the bottom, which is really making these things unit vectors. Good. And then that's multiplying 1, 1, 1, right? So this is the number on top. So let me get it. So it's, all of this is 4 plus 2 plus 0. So it's 6. And this piece here is 3. All right, so it's 6 divided by 3 times the vector 1, 1, 1. And we'll write that as, say, well, let's write as 2, 2, 2. Good. I've lost my behavior. This is not good. So we're subtracting this off. What am I doing? So this equals 4, 2, 0 minus, I'll leave this 6 over 3, 1, 1, 1. Right, so this is pointing the direction of, right, this piece here is pointing the direction of A1. This is our original A2, and we're subtracting this piece off. So let's get it. So it's going to be, we subtract 2 from every entry. So 2, 0, minus 2. Right, and so you can see that Q1, so far 1, 1, 1, and 2, 0, minus 2, they're at right angles to each other. So let's do that, maybe add a little thing. So these are orthogonal. That is the plan, right? So we've built the first one. Then we do it again. Okay, so it's going to be a similar looking thing. It's a calculation you should be able to do. So everything looks the same now. We've got A3, so we're going to have 1, 1, 1. Right, that's our Q1. Dotted with A3, which is this 5 minus 4 minus 7. So it's a similar looking thing. 1, 1, 1. Similar to what's up here. We've got this one. Now that is what is pointing in the direction of 1, 1, 1. And then we subtract off. Now it's Q2, which we've just made. 2, 0, minus 2. Again, this is the thing we're trying to clean up. 5 minus 4 minus 7, that's here. This is in the direction of 2, 0, minus 2. All of this is divided by the inner product of the second new vector, new basis vector. So what have we got? So on top, 1, 1, 1. If you multiply anything, right, 2 vectors together, or a matrix, right? If you have all ones here, it's basically saying just sum it all up. So 5 minus 4 minus 7. Right, so we get a minus 6 there. I'm going to put it like that. And then there's a plus 3 here. And over here we've got 2, 0, minus 2, so it's 10 plus 14, so there's a 24. And 2, right, this thing here, we've got a 4 plus 0 plus 4, so there's an 8. Good. So I think I can write out the next step. Without jumping too much, 5 minus 4 minus 7. right? So there's a minus 6 over 3 times 1, 1, 1. And then minus 24 over 8 times 2, 0, minus 2. Good. Right, of course, these are simple things. This is a 3 and this is a 2. So if we go through and combine everything properly, so we've got a 5 minus 2 minus 6. I believe that's right. So we've got a minus 3. Something went wrong there. That's a minus 3. And did I make, yeah. Of course, we're subtracting off, right? So this is a minus 6 over plus 3. So I've left this off. This is a plus 2. Oops. Good. Let's get that right. Right, this whole thing is a plus 2. And this whole thing here is a minus 3. Maybe I'll write it like that. Hopefully that's not too confusing. Okay, so we end up with a 1 plus 1, so 5 plus 2 minus 6 is plus 1. So then there's minus 4 plus 2, so we've got a minus 2. And there's a 0 over here. And then we have minus 7 plus 2, so it's minus 5. And then plus 6, so we've got back to 1 again. Okay, 1. So all of that is Q3. Let's check. This thing is at right angles to this one, right? So dot product, the 2 and the minus 2. And it's at right angles to the first one here. 1, 1, 1 is at right angles to, yep. Good. So let's put all the pieces in. So I'm just going to normalize, divide by their lengths. So 1 squared plus 1 squared plus 1 squared, square root of that. It's 3, right? And then we get a 1 over, so it's 2 squared plus 2 squared, so it's 8. Just write it like that. It's true, we could simplify that a little bit. And then the last one is here, so this is Q3. And that was a 1 minus 2, 1. So 1 squared plus 2 squared plus 1 squared, so it's 1 over root 6. Okay, good. This doesn't look like we've... So I'm going to show you in the next episode how we can factorize. What we're going to do is factorize this. This is going to be a matrix term, and we're going to write this as a factorization involving these q's. That's coming next. So at the moment, it's just sort of things are just sitting around. Let's just make this one a little bit cleaner. This one, this is a 2 root 2, right? Square root of 8 is 2 root 2. So this could be written as, the 2's will cancel. So 1 over root 2, 1, 0, minus 1. The others we can't do anything particularly nice with them. It's true. So note that the gram-schmidt method and then we'll see this a little bit with some of the things coming up, just has to produces square roots, tends to produce, because of this Pythagoras business, tends to produce many square roots. It's okay. They'll be sitting on the bottom, right? 1 over root 2, 1 over root 6. We'll just get those, their lengths. So that's mainly what I needed to show you for this. So that's this calculation here. Perfect, right? So this is a very standard thing to be able to work through, to understand. We've brought projections back. They're in play again. There was the basic projection idea, and then the more elevated one where we use projection matrices. So we're going to use that formalism to do something nice theoretically in a second. But we can also, and so that's note, that's one piece, and check, if you like, the Q1 transpose Q2, write it like this, equals Q2 transpose Q3 equals Q3 transpose Q1. We'll make them go around a little cycle. But in general, we need every pair, right? Equals 0, right? Right? Every pair of basis vectors right? They must be orthogonal. They must be orthogonal. So we've kind of guaranteed that by the way we've built it. We should then also be able to reconstruct the A's. Right, so just as we did with LU decomposition, we want to be able to make A again, right? We need to be able to rebuild A. So this is kind of the next idea. Next, C, A can be rebuilt. Well, I won't say it yet. So C, the A's right, can be rebuilt. This is often what we do, right? We break something up and then we rebuild the original thing from what we've made. Rebuilt from the Q's. And this gives us a factorization, and I'll just write it here, A equals QR. It's going to be the next piece, but I just want to put these things here. So this is Mn, this is n by n, so these are the same shape, and this is n by n. Right, that is the plan. Cool.